Well, going back to some of the technical innovations you were discussing, you've mentioned a couple of times the idea of the accessing the second electron. Could you explain a bit more about what that means and what the implications would be accessing that second electron?
Yeah. Um, so just to take a step back, so the audience understands a
Mhm.
little bit of the manganese dioxide reaction. So the manganese dioxide is very unique in alkaline electrolyte, especially electrolytic manganese dioxide and bernesite, which is another polymorph of manganese dioxide. It goes to through two electron reactions, with the first electron being a proton insertion reaction, where protons from your electrolyte intercalate inside of the manganese dioxide structure. And that's how you get your first electron capacity, which is approximately 308 milliamp hours per gram. The second electron reaction is a dissolution precipitation reaction, which is a flat shaped curve. And you get your other 308 milliamp hours per gram of capacity from that second reaction. Now, in the primary battery industry, they have always used the first electron reaction. They have never used the second electron reaction, uh, primarily because it's very uh, difficult to control the second electron reaction. There are different side reactions that take place which limit the capacity
Mm.
of that second electron. Um, so that's just an interesting tidbit. When I said the primary battery can give you 400 watt hours per liter, it's primarily the first electron reaction that I was talking about. If you can access the second electron reaction, you can get greater than 500 watt hours per liter. It's uh, it's a that means the battery chemistry is very high energy density. Now, the second electron reaction, since it's being dissolution precipitation, it's very hard to control the reactions that take place. And sometimes they lead to side reactions forming inactive substances which are not accessible electrochemically. And they're sometimes called as spinels, like osmanite or heterolite, which is just Mn3O4, or the zinc variation, which is ZnMn2O4. So the second electron reaction is something which people have been working on since the 1950s. That's where prominent researchers like Carl Kodesh, uh, who was at Union Carbide, tried to work on this second electron reaction. But eventually they settled on the first electron, and that's how the primary battery was born in the 1950s from Union Carbide, which eventually started its business, which is called EverReady, selling primary batteries, which eventually became Energizer. Just a little bit of uh, historical tidbit over there. Then Ford Motors tried to look at this second electron in the late 1970s, 1980s. There's a researcher called Helena Roblova who was trying to use it for EVs at the time, who believed that there's enough energy density in this chemistry to be marketed for electric vehicles, maybe. But again, history has it. It's lithium-ion batteries were commercialized in the 1990s, and then uh, it is what it is. What we tried to do in the 2010s was that we could use this for grid storage applications. That's where my work came into accessing the second electron reaction. And what I found was basically it was a resistance issue and controlling these side reactions that take place in the solution. So by using additives like copper and bismuth oxide, we were able to limit the side reactions that take place in the solution and reduce the charge transfer resistance, which allowed us to access the two electron capacity completely. That's what we published in Nature Communications in 2016. So uh, it's it's a breakthrough in the sense that you are able to access the full two electron capacity of manganese dioxide. And that's something which has not been done before. But that also brings other questions. What else is needed to bring this to the market? I'll foresee your other question, Emily, and go ask myself the question as well. And there are, of course, like I said, other things that you need to work on, and that's where the gelled electrolyte comes into uh, being very important, along with electrolyte additives, and then the separator, which
Hmm.
is to control zinc as well as copper ions in your solution, which sometimes can limit the cycle life because of metal deposition. So that's basically the history of the second electron, which, I believe that the CUNY Energy Institute and Urban Electric Power have played a pivotal role in discovering this. But now UEP is taking it forward by making um, other advances in electrolyte and separator to bring
Hmm.
this to the market.
Where do you think the second electron work is going to go? I mean, is it, would it, I'm trying to think of some way. I don't want to put any words in your mouth here, but like, is it going to give us twice the energy density from this kind of chemistry? I mean, what's the dream scenario for the second electron, target?
Yeah, so basically, we do expect twice the energy density out of this because you are accessing the
Mm-hmm.
two electron capacity, which is a very high number, right? So when you compare it to just the cathodes in lithium ion chemistry, right? So it's usually in the range of 100 to 200 milliamp hours per gram, depending on which cathode material you're using. And I know they're making progress with accessing a little bit more of the lithium cobalt oxide or a little bit more of the NMC, same likewise with the LFP. But when you just put that number up, which is 600 milliamp hours per gram, that's a very high capacity of the manganese dioxide cathode. Likewise, with the zinc, it's 800 milliamp hours per gram. So, you need both of them, right, to work together. It's like a marriage. You want both the cathode and the anode to work together and gel with each other to make this battery chemistry work. So it's not only making advances with the cathode, it's also making advances with the anode, where you want to access a higher utilization of your zinc two-electron capacity as well. So like you guys very much know as well, zinc has approximately 800 milliamp hours per gram in terms of its theoretical capacity. So we have been doing research in increasing the utilization of that anode as well. And we are trying to marry both of these very high capacity materials into one chemistry.
Hmm.
And both of them are solution mechanisms, where they dissolve into the electrolyte and they plate. So you can just imagine the complexity of this chemistry, basically, right? Uh, so but we are getting closer to making this work. We are making advances. We do believe the gel electrolyte is going to play an important role, and additives as well in the electrolyte, which I think companies like yours are very important, bringing in both new additives which are not being disclosed in prior literature, which allows us to control the deleterious side reactions that take place with zinc. Gassing is one of those main side reactions. Um, so we do think this chemistry can be used for very high rate applications, which we have shown in our manuscripts and in our testing, and also long duration energy storage. Where it can discharge over a long period of time and uh, not affect its cycle life. We have shown this in the labs, in our labs, and we are working to show this in battery level modules and see what kind of other things do we see when we put them into battery modules and then eventually into systems.
Yeah.
Yeah.
We totally agree. I think, on the importance of these systems. I think they're based on materials that kind of, the energy is in there, like the safety is in there, the supply chain is in there. It's all inherent to the materials that we're building with here, and it's just a matter of getting the combination right, getting, in our case, the right additives there to kind of help shut off. Most of the things that are going wrong are side reactions, are unwanted things, and in some ways, I think stopping those can be a very subtle science. That's all we got to do. I know we spend a lot of time doing it, right? So it's a complex question, but I mean, we shut off those unwanted side reactions, and then all that potential, kind of comes to the top. So it is exciting to see where these things could go, and really encouraging that you have batteries that have market need now that can be introduced in economies like India that are very particular about the kind of costs and needs. And yet there's so much more room for the improvement. I mean, we could have batteries in the markets that make sense today, and then when things break through on second electron, could outpace lithium chemistries and other sorts of applications. So it's a great kind of footing, kind of like a floor for these things that can do today, but a huge amount of promise for what they could do tomorrow too. So it's an exciting combination of things.
No, you're right, Onus. Like even the first electron, it has market applicability, like what you just now said, and the first electron is displacing lead acid chemistry, incumbent lead acid chemistry. And both the electrons have its usage, and I think the second electron reaction, like you rightly pointed out, brings it in competition with lithium-ion chemistry, so it's this. So there is room for development. There is a next generation product. There's considerable white space to target, and people to contribute and develop this chemistry further, basically.